All right, so I'd like to first thank the organizers for the invitation to speak here. It's really a great honor. I will be talking about inflation in string theory, and I don't think I need to remind this audience that inflation is a remarkably successful effective theory. Its generic predictions of an almost scale invariant, almost Gaussian primordial spectrum continue to be in excellent agreement with data. And one of the founding fathers of inflation, who is here, should be very pleased with how well his theory is doing. Okay? Now, effective as it might be, inflation actually is sensitive to Planck scale physics. And one way to see this is to note that the type of potentials suitable for inflation is very sensitive to its UV completion. Even a small dimension 6 Planck suppressed operators can give an order 1 corrections to one of the slower parameters and stop inflation. Okay? So without knowing anything about its UV completion, we can't say for sure that we have a viable model. Now, turning this argument around, inflation is an excellent opportunity for string theory. With a concrete quantum theory of gravity, we can assess whether these quantum corrections are going to spoil the nice properties that we want for inflation. In some cases, we can argue that these quantum corrections are small, and in some other cases, we may hope to even argue that these quantum corrections are absent. Now, this UV sensitivity that I mentioned is general for any models of inflation. But as I will now argue, models that give rise to a detectable level of gravitational waves are even more sensitive to UV physics. Now, there was, unfortunately, a false alarm last year about a possible detection of primordial gravitational waves. By now, it's pretty clear that a claim of discovery is premature. But with many experiments going for these observables, many of them are ongoing, some of them are going to be launched in the near future, it's not inconceivable that primordial gravitational waves with a tensor to scalar ratio of the order of 10 to the minus 2, or maybe even 10 to the minus 3, may be detectable in the not-so-distant future. So while many of us are disappointed that it has not been detected yet, it's still worthwhile to explore what the consequences would be if a detection is made by any of these future experiments. Now, a detection of primordial gravitational wave at this level not only point us to high-scale inflation with an energy scale of the order of Guts scale, not far from where we expect string theory or quantum gravity to come into play, a very simple argument due to David Life suggests that the infraton field range was super Planckian. Okay? Now, this strong UV sensitivity is what motivates us to consider inflation within string theory. And I should mention that the Life bound is not very sensitive to the precise value of the tensor to scalar ratio. Even if R is eventually measured to be a tenth of the value allegedly reported by Bicep, we would have come to the same conclusion. The important point is to detect this primordial gravitational wave. If the gravitational wave is at the level of 10 to the minus 2, or maybe 10 to the minus 3, we would have come to the same conclusion. Now, we will refer to models where the infraton field range is bigger than the Planck scale to be large field inflation models. Okay? And over the years, many excellent ideas have been proposed, including a very simple chaotic m² phi² inflation model, or the so-called natural inflation model, which involve axions. Now, chaotic inflation, m² phi² inflation, or natural inflation are radioactively stable. They are stable against quantum corrections. If gravity and infraton are all we have, there's nothing wrong about that. But the UV completion of general relativity typically include many new degrees of freedom. In the case of string theory, this UV degrees of freedom includes the Kaluza-Klein states, the string states. They are very heavy. But when you couple the infraton field to these UV degrees of freedom, typically, the infraton potential would receive an infinite number of corrections suppressed by this heavy energy scale. It would have been OK if the infraton field range is subplanckian. But if the inflaton field range is bigger than the Planck scale, as you integrate out these heavy degrees of freedom, after the inflaton moves a super Planckian distance, it will see a very big difference from the type of potential that you start with at the origin when inflation begins. So the message that I would like to emphasize here is that while a low-energy effective field theorist could claim victory by tuning the parameters in the Lagrangian to be small, or by postulating a global symmetry, a string theorist has to meet a higher level of rigor before we can make similar claims. Now, we can be more specific and consider axions. As you know very well, axions are natural inflaton candidates because they enjoy a shift symmetry that is perturbatively exact and is only broken by non-perturbative effects. So naturally, the energy scale associated with these non-perturbative effects is suppressed by the instanton action. Okay. Moreover, the continuous symmetry that you start with is broken to a discrete one. The potential generated by these instanton effects is a periodic potential with a periodicity that is set by the axion decay constant. Now, the very popular model, natural inflation, amounts to keeping only the leading instanton terms, so you have a very simple cosine potential. And it's quite obvious that the inflaton potential is flat enough for slow roll if the axion decay constant is bigger than the Planck scale. Now, you can justify dropping the higher instanton terms if you can show that the instanton action is sufficiently large. So the leading instanton effects will suffice in that case. The question is whether both conditions can be satisfied simultaneously, namely that the product of the axion decay constant and the instanton action that I call M over here is bigger than the Planck scale. Okay. So right away, we won't expect the product of the instanton action and the decay constant to be arbitrarily large. Because in the limit, when the product becomes infinite, we will recover a global symmetry. And quantum gravity does not like this to happen. So to get a handle on how the product can be bounded, we turn to a concrete quantum theory of gravity, namely string theory in this case. Now, in string theory, there are many axion candidates. The axions arise from higher form fields. Just like the usual one-form gauge fields, these higher form fields enjoy a gauge symmetry. Now, when you dimensionally reduce these form fields to 4 dimensions, let's say you have a 2-form gauge field, you reduce it on a 2-cycle, you get the pseudo-scalar in 4 dimensions. And the shift symmetry that you are looking for comes from a gauge symmetry in a higher dimensional theory. Okay? So it looks like we are in pretty good shape. There are many, many form fields in string theory. There are many, many internal cycles. We have lots of candidates for this, for axion inflation. And they all enjoy the shift symmetry that we are going after. Unfortunately, some careful studies surveying different formulations of string theory done about 10 years ago have concluded that axions with the properties that we want, namely super Planckian decay constants, do not seem to arise in any control limits of the theory. Okay? It's not that we cannot get a large axion decay constant, but if the axion decay constant is large, you are in a regime that the higher instanton effects could become important, or there could be some additional states that become light, precisely in this region of the moduli space. So that seems to be a rather general property of axions that arise from this concrete quantum theory of gravity. Now, there are 2 broad mechanisms that have been proposed to get around this problem. One is what you might call the communist approach. If one axion does not get you to super Planckian distance, many of them together can, and each of them contributes to the common good. Now, earlier ideas of this type include inflation and axion alignment. Okay. I will say more about this shortly, what these mechanisms mean. But by now, there are many, many more variants of ideas along this line. And in each of these cases, different field directions were identified for the collective efforts of the axions to go superplunking. Okay? The kinematic field range of the axions is enhanced. There's no question about that. But there's no guarantee that the UV corrections are under control. Okay? But this needs, of course, to be checked. But putting this aside, we find that there is a whole slew of models with large axion, effectively large axion decay constant. Another way to get around this problem is Axion Monodromy. Okay? And this class of model is fundamentally different from the previous type in two ways. One is that only a single axion is involved. You don't need to invoke thousands of axions. And the axion has already a mass at the perturbative level. Okay? So the axions in Axion Monodromy is not really an axion in the traditional sense. Its field space is non-compact. So as you go around the circle, you don't return to the same point. And in other words, the axions already pick up a mass at the perturbative level. Okay? Now, this property that the axion has a perturbative mass turns out to be very important later on, as some of the arguments that I will make on the multi-axion system, as you will see, do not apply to such non-periodic axions. Okay? So let us take a closer look at some of the multi-axion scenarios that have been proposed. Let's start with a simple example with two axions. Let's call the axions phi and rho. If you have two axions, and if you have two instanton-generated potentials, generically, both axions will pick up a non-perturbative mass. However, if the axion decay constants can be tuned such that only a linear combination of these axions is massive, while the orthogonal direction remains a flat direction, you could ask, what is the field range in the orthogonal direction? The field range in the orthogonal direction is infinite because there's no potential. Okay. Now, this is not what we want, but you can easily convince yourself that if you perturb this relation slightly, you can obtain an effective field range that is much bigger than the Planck scale. Okay? So in the limit, when these decay constants are so fine-tuned, you have a flat direction, the field range is infinite, but you can just, depending on how big the decay constant you want, you can just perturb these relations. And if they're approximately equal to each other, you find that the effective field range can be much bigger than the Planck scale. Now, in the case of inflation, you don't tune the model parameters, but rather you choose the direction in field space to inflate. In the case when you have n axion, you can go along the diagonal direction. And in the case of two axions, you see that the field range is enhanced by a factor of square root of 2. If you have n axions in the n-dimensional axion space, you can enhance this effective decay constant by a factor of square root of n if you go along the diagonal direction. Okay? Now, if you imagine that you have thousands of axions, the effective decay constants can be bigger than the Planck scale, even though each individual decay constant is of the order of the Gutt scale. Okay? And now, you can generalize these ideas by combining them and including all possible effects that you can think of. For instance, kinetic mixings. The axions do not have to be, the kinetic terms for the axions do not have to be in a diagonal basis where the potential is diagonal. So you can include these kinetic mixing effects. You can combine the two previous effects that I mentioned. And you can also invoke properties of large N and carry out some random matrix study. And one finds that by doing so, you can enhance the field range by an even stronger factor with the number of fields. In some cases, the effective field range can even depends on the number of fields exponentially. So it looks like, even though the individual decay constants are subplunkian, seems possible that the effective field range for a multi-axion system can become superplunkian. So the question that we would like to ask is whether there is a fundamental reason that in the single axion case, we seem to find from exhaustive searches that the product of the axion decay constant and the instanton actions to be bounded by the Planck scale. And if there's a reason why this is the case, we would like to know whether multi-axion models or models with monodromy can evade this reasoning, and how do we evade this reasoning? Okay. So this is where we bring the weak gravity conjecture into the discussion. So there are reasons why the weak gravity conjecture is referred to as a conjecture rather than a theorem, because like the folk laws that global symmetries cannot exist in quantum gravity is not proven, the weak gravity conjecture is also one of those folk laws that are not proven. Nonetheless, the conjecture is motivated from black hole physics. It is consistent with what is known, and there seems to be no counterexample that has been found. Okay? Now, we are going to take an agnostic view on whether the weak gravity conjecture is truly a consequence of quantum gravity. Instead, we will take the weak gravity conjecture as a starting point and try to derive its consequences on inflation. Okay? Now, the weak gravity conjecture was first made by Galileo. The conjecture was that because gravity was so weak, the Pisa Tower is still there after 800 years. But this is not the weak gravity conjecture that I would like to refer to. The weak gravity conjecture that I refer to is the statement that gravity is the weakest force. Namely, that for every long-range interaction, there must exist a particle with a charge that is bigger than its mass in Planck units. Okay? Now, this order 1 factor was left rather vague in the conjecture, but as you will see, we have made this order 1 factor more precise in our work. So how do we understand this conjecture? Well, a heuristic way to understand this conjecture is to consider a U1 gauge theory that violates this conjecture. Namely, if you have a U1 gauge theory that has only particles with a charge that is smaller than its mass, what would happen? Okay? If that's the case, you'll find that the gravitational attractions between these particles is stronger than the gauge repulsion. So these particles will form bound states. And these bound states are stable because there's nothing lighter for them to decay into. Okay? And you can convince yourself that you can form infinitely many of these bound states. Now, the presence of infinitely many stable bound states may lead to problems with remnants. Okay? I will say more about that later on. But from this heuristic argument, you can understand what this 1 in the weak gravity conjecture corresponds to. The 1 in the weak gravity conjecture corresponds to the ratio of the charge and the mass of an extremal black hole in the theory under consideration. Okay? So the weak gravity conjecture basically said that you must be able to find a state with a charge to mass ratio that is bigger than the charge to mass ratio of an extremal black hole. Otherwise, this infinitely many stable bound states have no channels to decay to. Okay? Now, as I said, the conjecture is a conjecture. The statement is still being formulated. There's still an ongoing discussions of how to make this statement more precise. And there are several versions of the weak gravity conjecture that have been put forward. The strong form of the weak gravity conjecture requires these states that satisfy the inequality to be the lightest charged particle in the theory. And this is motivated by the spectrum of states in perturbative string theory. Now, the weak form of the weak gravity conjecture only requires the existence of such a state. Doesn't matter who these charged particles are, as long as you find a charged particle that satisfies this inequality, then there's nothing wrong with coupling this theory to gravity. Okay? And the reason why one might expect a stronger form of the weak gravity conjecture is that quantum effects are important for making a state super extremal, meaning that the particle's mass is smaller than the charge. Okay? And the lighter the states, the more important are the quantum effects. And in the case of perturbative string theory, this quantum effect is the Kashmir energy. So when you quantize the string, when you look at the oscillators, the commutators will give you a negative number, and that's precisely what makes the state super extremal. Okay. 10. Okay, so what does the weak gravity conjecture has to do with axions? Okay? Naively, if you can generalize this conjecture to p-dimensional objects coupled to p+1 form, then with the replacement of mass by the tension of this object, it seems possible to explain the difficulty in finding super-Planckian decay constant in control limits of the theory. Okay? And the reasoning goes as follows. You can, loosely speaking, think of the inverse of the decay constant as the charge, and the instanton action as loosely the tension. Okay? And if you make that extrapolation, starting from the weak gravity conjecture, you arrive at this inequality, which seems to be consistent with what was known from the exhaustive search of super-Planckian decay constants in string theory. However, this argument is harder to make with instantons rather than particles because it involves bound states and the decays. Okay? And so that's the reason why we set out to find evidence for the instanton versions of this weak gravity conjecture. Okay? So is there a way to derive something like this with the instantons? Now, we can get some handle on this question using T-duality. So T-duality is a symmetry of string theory. It maps a theory with a given size to a different theory with inverse size. And not only is it a symmetry of the spectrum, it's also a symmetry of the interactions. So to be concrete, you can say you start with an axion in type 2b string theory that coupled to the instantons. This is what gives rise to its non-perturbative potential. You can take one of these non-compact directions, compactify it on a circle, then T-dualize and decompactify. So under this chain duality, which is known as the C-map, you are mapped to a type 2A string theory, and the axions becomes the U1 gauge field, whereas the instantons becomes the particles. Now, we see from this analysis that the naive expectation of how the weak gravity conjecture applies for instantons holds up. The instanton action and the inverse of the decay constants are mapped to the mass and the charge up to these factors which are hard to guess without doing a calculation. Okay? But naively, there's a problem because under this C-map, the coupling constants become infinite. Okay? So starting from a weak coupling theory, you end up with a strong coupling theory in type 2A. But this is not the end of the world. We know how to handle this in string theory. The strong coupling limit of type 2A is M theory. So instead of formulating the weak gravity conjecture with type 2A string theory, we can do so with M theory and ask what is the charge to mass ratio of an extremal black hole in M theory compactifications down to 5 dimensions. And this is what we find, at least for this particular case of axions. So the statement we could make is that for an axions that come from a Raman 2 form in type 2B string theory, we find that the product of the axion decay constant and the instanton actions to be bounded by these precise factors of the Planck scale. Okay? Now, we can also work out the corresponding bound for axions coming from other form fields in other formulations of string theory. They give you different order 1 factor, but they all seem to fit into this inequality of this form. So in a concrete sense, we have made the weak gravity conjecture precise. Now, you can generalize these discussions to multiple axions. And again, it's useful to go to the dual picture with U1s and charged particles. And let's consider 2 U1s, or 2 axions. So there must exist at least 2 charged particles for this black holes to decay if you have 2 U1s. And as suggested by the single axion case, we are instructed to consider the following charge factors in a 2-dimensional space. The extremal black hole lies on a sphere with a given radius. And to simplify the formula, we normalize the radius of this extremal ball to be 1. And all the charged black holes lie within this sphere. Now, naively, it looks like we only need to find a state with a charge to mass ratio bigger than 1 in each of these charge directions, and we are done. But this is not the case, because if you consider a black hole with a charge in some other directions in this 2-dimensional charge space, there are some black holes that still cannot decay. So you need to find states with a bigger charge to mass ratio to account for these other black holes. And the more precise statement is that the convex hull generated by these charge vectors should contain the extremal ball. The convex hull is the shaded region here. Okay? Now, these charge vectors do not need to be orthogonal, as I have shown on this slide. The only thing that is needed is that the extremal ball is contained within the convex hull. So you can find other examples. If you were able to find states with this particular charge to mass ratio, all the black holes under considerations can decay. So in this picture, the aligned axion scenario corresponds to choosing charge vectors that almost align, but the extremal ball is not contained inside the convex hull. And in the case of inflation, the charge vectors need to be enlarged by a factor of square root of n in order to contain this extremal ball. And this basically undoes what you gain, the factor of square root of n that you gain by going diagonally. Okay? And our discussion is not limited to the special cases. We have shown quite generally that given a set of instantons that give us a super Planckian diameter in the axion field space, no matter how complicated the kinetic terms are, the extremal ball is not contained inside the convex hull generated by these instantons. Okay? Now, the weak gravity conjecture is a conjecture. If you don't want to use a conjecture to constrain a model, you can ask whether gravitational instantons can induce sizable higher harmonics to the axion potential and spoil the properties of super Planckian field range. This was recently done by the Madrid group, and the conclusion basically agrees with ours. So in the remaining 5 minutes or so, let's see whether there's a way out. Okay? Now, we were very careful in choosing the word fence in our paper and not walls, because there are loopholes. There are interesting loopholes that we find that could potentially help us evade the problem that I mentioned. Okay? Now, first of all, the weak gravity conjecture requires only the extremal ball to be contained inside a convex hull. It doesn't care who these charge vectors are. So you could imagine that in addition to the instantons that give you the infraton potential, suppose there's an additional instanton that gives the negligible contributions to the potential, but with a very small decay constant, such that this criteria that we find earlier is satisfied. So in the presence of these spectator instantons, the convex hull conditions can be satisfied. So there's, the weak gravity conjecture is not violated. Okay? And notice that the instantons being heavily, these instantons are mapped to a very massive particles in the particle picture, okay? Because the instanton action is very large in Planck units. So they do not correspond, these spectator instantons do not correspond to the lighter states in the theory, so the strong form of the weak gravity conjecture is still violated. Okay? So which form of the weak gravity conjecture should be satisfied in a consistent quantum theory of gravity? So recall that the weak gravity conjecture is motivated by black hole physics, and in this context, it was argued long ago that having infinitely many stable remnants in a finite mass range could lead to pathologies. Basically, you can go to an accelerator frame where you find that you have a thermal bath of infinitely many species, and the entropy diverges. The weak gravity conjecture is a stronger requirement. The weak form of the weak gravity conjecture states that having infinitely many stable remnants, even within an infinite mass range, are still not acceptable. And the strong form of the weak gravity conjecture requires these remnants to decay to the lighter state. Now, the loophole that I mentioned amounts to hiding our ignorance about the spectrum of states at or above the Planck scale. Okay? So a priori, there's nothing wrong with that. But let me remind you that the whole purpose of realizing large field inflation in string theory is to tame the UV sensitivity. And this sort of defies the purpose. So I think the burden of proof is on those who claim to find a viable model of large field inflation in string theory. So let me also mention that, and it should be obvious to you, that the constraints that we find on the multi-axion systems do not immediately apply to Axion Monodromy, because the axion in this case is mapped to a very massive, is mapped to a massive gauge field. However, there are non-perturbative processes that could take us to a different branch of the potential. Even though inflation takes place on one of these branches, there are non-perturbative effects that could take us from the inflationary branch to some other branch. And suppressing these tunnelings could lead to potentially an interesting bound on the infotron field range, or in other words, the Tesla-to-scalar ratio. So let me just conclude. I have illustrated the UV sensitivity of inflation, especially for models with detectable level of gravitational waves. And we have made the weak gravity conjecture quantitatively precise for axions. As long as you can dualize the axions to U1 gauge fields, our diagnosis would apply. And this allows us to put constraints on large field inflation models with axions in terms of the convex hull. Now, although the weak gravity conjecture is motivated by black hole physics, both the strong and the weak form are not derived from first principles. So it would be interesting to firm up the statements. And if the weak gravity conjecture in the strong form is truly a consequence of quantum gravity, then several large field inflation models are ruled out.